of x is the notation for expected value. And what I did was I put expected value sort of like in my own words, like what does expected value mean? Expected value is not a probability. It's a long run average of what should happen if you run your experiment lots of times, or we're going to be playing games, if you play your game a lot of times. Okay, what we expect to happen over a long period of time. Many, many trials. This is a section that's not covered in the textbook, but we're going to learn it because you might see on your gold sheet next week we're going to be doing our Chapter 9 project, which is our game day project. So maybe you know somebody who's already taken honors pre-calculus. You guys are going to be working in groups to create games. You're going to calculate the probabilities of your games and the expected value of your game. And then I think it's Thursday of next week we run the games in class. We'll be wagering Tootsie Rolls. And we'll see if the game ends up the way you thought it would. Okay, so that's going to be very exciting for us. So this stuff is included on the notes page. Okay. When you calculate probability or expected value, it's best for you to create what we call a probability distribution. And the probability distribution is that little table, and it's got two rows to it. One of the rows is probability. The other row are values. And we're going to call them like x sub 1, x sub 2, x sub 3, and so on. Okay. Now, what those values represent, usually we calculate the expected value of the player. They're the values to you as a player if you go up to a game. So you might have to pay to play the game, or you make a bet on the game. And then what the value represents is what you walk away with. Did I come away with more money, so I have plus 2 Tootsies? Did I lose my Tootsie, so I'm walking away minus 1 Tootsie? Those are the types of things that you're going to put into the value section. In a probability and stats class, you may call those values random variables. Expected value is this little equation right here. I would maybe like make note of it, put a star by it or something. So this is how you calculate expected value. It is not a challenging calculation. It's like figuring out your probabilities that are like the toughest part of this. Okay. So expected value, where I said it was like the long run average, you can also think about it like a weighted average, where the weights are the probabilities of each value. Okay. So what you're doing is, whatever your first value is, multiply it by its probability, and then add that to the next value times its probability, and so on and so on. Different games will have different numbers of outcomes or values. It really just depends. Sometimes there's only 2 options, win or lose. Sometimes you might have 3 options, win, lose, break even. Sometimes you might have even more than that, like win 3 Tootsies, win 2 Tootsies, win 1 Tootsie, break even, lose. Okay, so you can have a varying amount of values in a probability distribution. It would depend on the scenario. Okay, and I kind of talked about everything in terms of games because that's where we're going to be putting it. But you can use expected value in other scenarios. Okay, so that's expected value. Now we're going to look at an example. Teach you a little bit about roulette today. I don't go to the casino very often. I don't have a lot of insight for you. Makes me nervous. You got to make a lot of decisions there. Okay, on the American roulette wheel, there are 38 slots. They're numbered 1 through 36, and there's the 0 and the 00. Half of 1 through 36 are red, and the other half are black, and then the 0 and the 00 are both green. This is the one where like it turns, and a little white ball drops in, and then when it stops turning, it lands in the slot. Suppose that a player places a simple $1 bet on red. We're going to keep everything very simple here because we're just learning about probability and mathematical expectation. So when we have game day, your players will only be allowed to bet 1 Tootsie. Like someone can't come up to your game and be like, I'm going to bet 100 Tootsies. Okay, we're going to keep it simple and everybody bets $1. Okay, or a Tootsie. A Tootsie. No money shall be exchanged on game day.
As far as you know.
I'm going to be watching. I'm going to have cameras up in the room. Okay. If the ball lands in a red slot, the player gets their original dollar back plus an additional $1 for winning the bet. And if it lands in a different color slot, the player will lose a dollar bet to the casino. So you're going to be asked to do these 6 problems for each of the games in Mrs. H's House of Humility there on the back. So you're going to run through these 6 things. Okay. So the first thing you want to do is state the sample space. Sometimes sample spaces are easier than others. And sometimes maybe instead of like just stating the sample space in the brackets, you want to actually like draw a tree diagram of your sample space. That might actually be more helpful than listing all the events in the sample space. So we'll talk about that more when we get to the back. What's the sample space in terms of this person coming up, betting on red? What are the possibilities when I turn the roulette wheel and the ball lands? Red, black, green. Okay. So we would list those in our sample space with the curly brackets. Red, black, green. Okay. What is the probability of winning? Emma, you say? 18 out of 38. Okay, and I'm going to go ahead and simplify that. That's 9 out of 19. Okay, and tell us where your 18 out of 38 came from.
Well, half of 36 is 18, and half of the 36 are red, and there's 38 total.
Excellent. So it's just basic probability, right? Okay. Now, depending on the games you create, you may have basic probability, you may have like consecutive events where you're multiplying probabilities, you may have to do permutations or combinations, just depends on what you create. What is the probability of losing? I heard a 20 out of 38. Where are we getting 20 out of 38 from? Oh, sorry, what's that? Oh, the complement. Okay, I like that a lot. In this case, aren't there only 2 options? Win, lose. So I'm going to mark that down. This will be 10 out of 19. And these 2 are complements. Okay. And so you could have calculated that either by taking like the 18 black plus the 2 green and getting your total 20 ways to lose. Or you could have just done the complement 1 minus 18 out of 38, and you would have still gotten 20 out of 38. When your probability of winning and your probability of losing are complements to each other, there is no break-even point. If your probability of winning and your probability of losing are not complements, do not add up to 1, you want to check, did you create an option for someone to break even? If you didn't create a break-even point, then maybe you have one of your probabilities incorrect. Maybe they should add up to 1. Okay, so we've got our probabilities of winning, losing, and if we had had breaking even, we could have said something about that. And now we're going to create that probability distribution. So remember, the probability distribution has our x's and our p's. And one thing that I want to point out, the values that go in for x are the value to you, the player, when you get the certain outcomes in the sample space, but the values in the probability distribution are not necessarily the values in the sample space. This isn't an issue for us because right now our sample space is colors. Okay? But in the next example, your sample space is numbers. And that doesn't mean that's what you get when you finish the game. So you have to think about it like, if I land on red in the sample space, what's the value to me as a player if I made that $1 bet? What do I walk away with? I walk away with $2, but what do I walk away with compared to what I came with? $1. It's a plus 1. Okay, so one value in this game is plus 1. And that's when it lands on red, which we know its probability is 9 out of 19. What's the value to me, the player, when I land on black? Minus $1. And what's the value of me, the player, or what's the value to me, the player, when I land on green? Also minus $1, so those could be combined, and they were combined here in our probability of losing 10 out of 19. So in this probability distribution, again, we only have two values. Win $1, lose $1. So remember, if you get your dollar or your Tootsie back, that's not, getting your Tootsie back isn't a win. It's just a break even. And to clarify with break even, I don't consider breaking even winning or losing. It's a whole separate group. Okay, to calculate mathematical expectation, we're going to find that long run average if we play the game many, many trials. So we're going to do -1 times 10/19 and 1 times 9/19, which of course I know fraction-wise is going to come out to -1/19. If you type that into a calculator, because we're betting $1, right? I'd like to know this in terms of money. This is going to be -0.05 cents rounded. I think it's like 0.052 or something like that. So, another thing, just a quick point to make. Expected value doesn't always have to match the values to the player. Like, do you agree? I can't go up and play the game one time, bet $1, and then lose 5 cents. I would lose a whole $1. So this is not for like a single trial. This is saying if I play this game many, many times, over time, it's going to be as if I lost 5 cents a game. So if we play the game 100 times, how much would you expect to win or lose? Just multiply the number of times played by your expected value, and that would be -$5. Now, I do also want to say another thing, because you'll see this language later on. This is your expected value for the player. Like the player is expecting to lose over time. You might sometimes see or read about expected value for the house. The house is whoever is like running the game, usually the casino. Okay, if we're working with casino games. So if my value as a player is -0.05, what's the value to the house? Positive 0.05. It's just the opposite of the player expectation. Okay? So if I play this game 100 times, I'm expected to lose $5. The house would be expecting to win $5. So let's just take a quick minute to think logically here. What would you assume about expected values for all games in a casino? They are negative so that the player loses over time, right? Because then, if we play the game many, many times, and think about a casino, people are in all day, all hours, right? Okay. They're going to keep playing that game, just keep played over and over again. Of course, some people win, but more people are losing, so the casino is making money. Okay. So, you'll want to be thinking about this next week when we get into game day. Just to kind of give you an idea. We're going to be wagering like 1 Tootsie. So usually most people's expected values are within the range of like -1 to 1. It can be higher or lower if you're like, or it can be higher if you have like payouts of 10 Tootsies or something like that for one of your events if they're really hard to get. But if you have an expected value that is like very close to -1 Tootsie Roll, so it's like -0.7 Tootsie Rolls or -0.8 Tootsie Rolls, that means that as we play the game more and more often, people are expected to lose a lot of Tootsies, right? So that means when they come up to your game, they're usually going to lose. That's not always a really fun game to play when you know you're going to lose. Okay? And the opposite is true. Some people have done their games and like they've done their calculations, but it's like as if you didn't even look at it. Their expected value is positive, and if you've got like a positive 0.5, that's meaning you're going to be paying out a lot of Tootsies. And when you think about that, if you go up to a game and you're always going to get Tootsie, I mean, yay Tootsie, but at the same time, in terms of gaming, that wasn't very exciting. So that's something you and your group members will be able to think about. Like, can you manufacture a game so that the expected value is challenging to win, so that it's interesting, but it's not so challenging that you can't win at all. Okay, so just kind of be aware of that. Okay, I'm gonna let you loose on 2 and see if you can fill in the blanks here, and then we'll come together and see if we agree.
Oh, I didn't see the 20. This is count.
Mm-hmm.
On example 2, would like the $1 and $5 still be considered winning, or is making money considered?
I would only consider winning if I walked away with more.
Okay.
Wouldn't you?
Yeah.
Getting my money back is not very exciting. I mean, I'm thankful. But I consider breaking even a whole separate set.
Okay. Well, that would be -4.
Did you do this math in your head? I would check your You have it. Yeah. Yeah. But I still don't agree with thinking it's too much. You said you did it in your head. Double check those. Yeah, the value is good. Okay, so I'm going to go ahead and debrief on this envelope game here. Most people did a great job with sample space, just like all the possibilities within the envelopes. There's $1 bills, $5 bills, $10 bills, and $20 bills, so list those out. The probability of winning, some people ask me, and I heard good conversations among the groups, what do you actually consider winning in this case? Gaining money. So that would be your 10 and your $20 bill. It would be wins. So you have one of each of those. So 2 out of 10 is 1/5. And then losing is when you walk away with less money than you had. So we would do just the $1 bill. Okay. And there were 6 $1 bills. So 6 out of 10 is 3/5. So notice that these two probabilities, 1/5 and 3/5, are not complements of each other, correct? That's okay, because we can see we have one envelope that is considered not winning and not losing. That's our $5 envelope. If I walk up, I pay $5, and I get my $5 back, no, I didn't win, I didn't lose. It's all the same to me. So if I ask about probability of winning and probability of losing, you're not going to answer anything about breaking even. However, breaking even will show up in your probability distribution with a probability of 1/5. What's the value to you, the player, when you break even? 0. Okay, so it's one that, like when you multiply it by its probability, it's going to be 0. So it's not super interesting, but it should be in there. Okay. So when I create the probability distribution, I know I've got a 0. This is that one where I wanted to make the point. The numbers that go into the values are not 1, 5, 10, 20, and I saw most groups did a great job with this. If you pay $5 to play the game and you get the dollar envelope, what's the value to you, the player? -$4. I mean, it's not so bad. I got $1 back, but I'd still rather have my money. Okay. So I'm going to have a -$1. I've got my $0. If I pull the $10, what's the value to me, the player? I'm going to get a +5. And if I pull the $20 bill, +15. So it's like I've paid them. This is not so much like a wager. I've paid them $5 to play the game, and then that's the value to me, the player. Okay. Eli. Yeah, my minus is kind of like over here. Sorry.
4 though?
Oh yeah, 4. Is that what you said?
Yeah.
I wasn't listening. I mean, I was listening to the question I thought you were going to ask me, and that's the question that you actually asked me. You guys do that, I'm sure.
Do what?
Selective listening. Okay, so then you can put in your probabilities. Losing was 3/5. Breaking even we know is 1/5. And again, I just want to point out, this can be an interesting thing. Where our probability of winning was 1/5 from the 2 tenths. That now needs to be separated in the probability distribution because I have tiers of winning, right? Different tiers. So this is 1/10 and 1/10. What did you guys get for your expected value calculation? Yeah, it should be -0.4. I'm just going to show my work here for my notes. And that's in money. So I should put my $sign there, -0.40, so 40 cents. And then if I play the game 100 times, what do I expect to win or lose? 100 times, -0.4, that would be -$40. I think you would agree, like, we could see where if we play that game a lot, that makes sense. We're going to end up losing a lot of money because there's way more $1 to pick. But at the same time, if we play a lot of times, we may pull some 20s, so that's going to like bring us back up to the top. Okay, but we're going to end losing quite a bit of money if we play this game. So how many people would be a risk taker and pay this $5? Oh, good. All my financially smart students. Whew. Good. Glad to hear it. Okay, how are you feeling about expected value so far? Pretty good? Got any questions for me? Okay, now, on the back side, this is where you're doing your homework. Do you notice down at the bottom it has like 6 questions? 1 through 6. Those are if you read those real fast, those are the same 6 questions on the front side. So like you're just doing the same thing we did in the examples for each of the 5 games. After you do the 5 games, then you go back and you do those reflection questions. Now, I want to talk about low, lower, and lowest. So real quick, will you read through low, lower, and lowest so you get an idea of the game? For low, lower, and lowest, writing out the sample space, like 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, is probably not the most helpful way, to actually, see what's happening. So I put down there in number 1, you can state the sample space, and you can use the tree diagram if you want. So I think the low, lower, lowest works really well with the tree diagram because if the house rolls a 1, I could roll a 1, 2, 3, 4, 5, or 6. And same if the house rolls a 2. And I can just kind of keep repeating that work as I go. And then how do I win low, lower, lowest? I have to be lower than the house. So then I can go here and I can say, based on my roll, if the house rolls a 1, do I win at all? No. Was there a break even? Yeah, if I match them. So then I could label this is a break even, but these are all loses. So there's 5 outcomes for losing, 1 outcome from breaking even. When I get to 2, now I have 1 win, 1 break even, and 4 losses. So that makes it a little bit easier for me to compare the 2. This is a win, this is a tie, this is a loss. Does that make sense? Feel free to use the table or tree diagrams if you want. I will post the answer key later today to this so that you have the opportunity to check it before you come to class tomorrow because you will take a quiz tomorrow for probability and expected value is on the quiz. So mainly when you're working through these questions, what you want to be able to do is create a probability distribution and calculate the expected value and then say how much you're expected to win over X amount of games. Okay. So make sure that you feel comfortable with that. Does anybody have any questions for me? Okay.